Hello everyone, welcome to Stat 441 at VCU. In this lecture, we will discuss how to create confidence interval for difference of means. Okay, so let's say we are interested in comparing two population means, and here's an example to start with. The means, let's say we want to compare the mean starting salary for college graduates with mechanical and civil engineering degrees. So we have two populations and we want to compare the two population means to find if they are different or if they are the same. What is the difference like? Another example, the mean operating cost of automobiles with rotary engines and standard engines, or the mean failure times of two electronic components. So we have two similar populations and we want to compare these two populations by using the mean. Okay, so the way we will start is we will have these two populations with means mu1 and mu2 respectively. From each of these populations, we select independent simple random samples. So basically, the first sample from population 1 of size n1, second sample from population 2 of size n2. And if you think about it, what will be if we wanted to create an interval for mu1 minus mu2, or if you wanted to estimate mu1 minus mu2, intuitively you know that from the samples we will collect the information of the first sample mean y1 bar and the second sample mean y2 bar, and the difference of the two sample means will be an estimate for mu1 minus mu2. The mean of the sampling distribution of y1 minus y2 bar will be expected value of y1 bar minus y2 bar, which is mu1 minus mu2. And the variance for these will be sigma 1 squared over n1 plus sigma 2 squared divided by n2. And this is again coming from the central limit theorem. Okay, so now basically because it's we can apply the central limit theorem here, we have an approximate normal distribution. The mean of this distribution will be y1 bar minus y2 bar, and the standard deviation can be given by sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. Therefore, the confidence interval can be created like this: y1 bar minus y2 bar plus and minus z alpha by 2 times the standard error or the standard deviation, which is this value here. If we wanted to calculate this for the cases where we have a large sample, but the population standard deviations are not known, we can still replace that with sample standard deviations, just like we did for a single mean or one population mean. So it's very similar in how it's set up, and we can compare the two means, mu1 minus mu2. Here are the assumptions. So the first assumption is that the two random samples are selected in such a manner that they are independent of each other. So that's one assumption. The second assumption is that both samples are large enough so that we can apply the central limit theorem. So n1 and n2 both should be greater than or equal to 30. Okay, so here's an example. We want to estimate the difference between the mean starting salaries for recent graduates with mechanical engineering and electrical engineering from University of Michigan. A random sample of 48 starting salaries from University of Michigan mechanical engineering graduates produced a sample mean of 64,650 with a standard deviation of 7,000. A random sample of 30 starting salaries for aerospace engineering produced a sample of 58,420 and standard deviation of 6830. Okay, we want to create a 95% confidence interval for mu1 minus mu2. Because it's a large sample, we will use this format: y1 bar minus y2 bar plus and minus z alpha by 2 for 95%. So remember, 1 minus alpha is 0.95. That means alpha is 0.05 and alpha by 2 is 0.025. So you can use the t table, the last line with the infinity, to find this value, or you can use the z table. Okay, so we'll just use the t table here. So remember, z alpha by 2 is z 0.025, and this will be the value 1.96. Okay, so plug in all the information. For sigma 1 squared and sigma 2 squared, we can replace it with the S1 and S2. This is the first sample mean, second sample mean. We have this interval. So if we calculate these values, 6,230 minus 3,085 will give us 3,145. When you add these, you get 9,350. So our confidence interval is between these two values, 95% interval. Now, if you look at this interval, both values are positive. Okay, so what does that indicate? It indicates that the starting salaries for mechanical engineering graduates are higher than the mean starting salary for aerospace engineering graduates. How do we know? Because it's mu1 minus mu2, and we are 95% confident that the differences between 3,145 and 9,315. So both are positive numbers, which means mu1 is higher than mu2. Okay, here is a quick chart to figure out which mean is higher or which one is lesser. So we can look at the interval to figure that out. So if the interval is such that both the values, LCL and UCL, the lower confidence level and the upper confidence level, both are greater than 0, then the first mean is higher than the second, or in general, the parameter. If you're, it could be any difference. So here it's mu1 minus mu2. It could be pi1 minus pi2, or sigma 1 minus sigma 2. So if you have a difference, this is what we will look for. So if both values are positive, then the first value is higher than the second one. If both values are negative, then the first value is smaller than the second value. So mu1 will be less than mu2 if both are negative. And if the lower limit is negative, but the upper limit is positive, that means the interval includes 0, then we cannot conclusively say which one is higher. Okay, now let's look at another scenario here where we do not have a large enough sample and we have a small sample. We can still create the confidence interval for mu1 minus mu2. This is mu1 minus mu2. I think this slide is not showing it correctly here. So based on this small samples, again, we can use the student's t distribution. Okay, and again, the assumptions here are that the samples are small, n1 is less than 30 and n2 is less than 30. Okay, here are the assumptions that we need to make sure. The first assumption is that the populations are approximately normal. The second assumption is that the variances of the two populations are equal. And the third assumption is that the samples are independent of each other. Okay, with that, this will be our confidence interval formula: y1 minus y1 bar minus y2 bar plus and minus t alpha by 2 square root of sp squared 1 divided by n1 plus 1 divided by n2. So this value here, sp squared, is called the pool variance. So this will be the formula to calculate the pool variance, and that's why we have the assumption that both the variances are approximately equal. So this is the weighted average of the two sample variances, and the weights are proportional to their respective sample sizes. So it's just basically, once you gather the sample, you will calculate the two mean values for the samples, and then you will calculate the two standard deviations, and then basically plug it into the formula. Here is an example. The The Journal of Testing and Evaluation reported on results of lab tests conducted to investigate the stability and permeability of open graded asphalt concrete. In one part of the experiment, 4 concrete specimens were prepared for asphalt contents of 3% and 7% by total weight of mix. The weight permeability of each concrete specimen was determined by flowing deaerated water across the specimen and measuring the amount of water loss. The permeability measurements for 8 concrete specimens are shown in the table. Okay, so this is the information we have. For 3% we have just 4 observations. For 7% we have another 4 observations. So now in this case, of course it's a small sample and we want to create a 95% interval. Okay, so what should we do? We will use the t distribution. So in this case, both samples are small, n1 and n2 are 4. The procedure requires the assumption that we have independent samples and the populations are normal. A 95% interval can be calculated using this formula here. So y1 bar minus y2 bar plus and minus t of 0.025. Again, it's a 95% interval. So 1 minus 0.95 is 0.05 divided by 2. So 0.025. And we can calculate a pool variance in 1 over n1 plus 1 over n2. So these are these are the values of the mean for the two data sets. These are the sample sizes. Okay, and this is how we can calculate the pool variance. n1 minus 1, so that's 3. That's 1 squared, so that's the first standard deviation, plus 3 times the second standard deviation squared, divided by 6. So that gives us this value. Now in this case, we still need to use the t distribution table to calculate the t alpha by 2 value. So we figured alpha by 2 is 0.025, but because there are 2 samples here, the degrees of freedom will be n1 plus n2 minus 2. So in this case, 4 plus 4 minus 2, which is 6 degrees of freedom. So from the table, for 6 degrees of freedom, we will figure out t 0.025, which is 2.447. So plug in the information and we have the interval. So here's the table, degrees of freedom 4 and t of 0.025, so 2.776. Okay, here's the final interpretation. We are 95% confident that the interval is -8 and 387 encloses the true difference between the mean permeabilities of the 2 types of concrete. Now, if you look at this interval, the first value is negative, this upper value is positive. That means 0 is included in the interval. So we cannot say conclusively if the population means differ. Okay, so that's confidence interval for 2 population means when they are independent of each other. In the next lecture, we will discuss how to create confidence interval for the case when the 2 samples are dependent on each other or they are paired with each other. All right, thanks for watching.